thank you very much for giving me this opportunity. So today, as he mentioned, I will talk about some hydrodynamic role of kinetic helicity, especially the kinetic helicity density, local density of kinetic helicity in large-scale structure formation or large-scale flow generation. Okay. Oops. Okay, so these are topics of my talk. And first, I will show some examples of flow beyond the scope of eddy viscosity. Eddy viscosity, I mean, so diffusive approximation for the Reynolds stochastic. Okay. Then I will very briefly show how to treat such hydrodynamic situation. And then I will explain some global flow generation mechanism. And then if I have enough time, I will talk about subgrid-scale modeling. So then finally, I will just make some concluding remarks related to turbulence modeling. And very often I use this cartoon. So this is by Foxeye. And as you may know, so many blind person touches a huge elephant. Then they thought, they think this is the essence of this animal, elephant. But they just treat some part. Okay. Then what I meant to say here is that not at all your work is useless, okay? But I just would like to say the collaboration with other field people is very important in order to get some general picture of in my talk. The subject is how to say turbulence or large-scale flow generation, something like that. And also very often I use this view graph. Then in order to get some information for turbulence field, of course, we have to consider the fluctuating field. Then we just divide the field, any field, into mean and fluctuation. And in my talk, capital letter means mean field in any sense. And also primed one means fluctuation. Then even if we treat large-scale mean field, of course, we have a turbulent correlation. Then we have to start to consider fluctuating field. And this is just a fluctuating field. In this particular case, I just consider solenoidal incompressible hydrodynamic as a simplest possible case. Then, of course, it contains turbulence mean interaction and also turbulent interaction. And very roughly speaking, there are two approaches. One is so-called, I often called instability approach. They just drop nonlinear interaction between turbulence, then start to consider this fluctuating equation. Of course, the presence of large-scale inhomogeneity is a matter of course in this approach. Then we can argue this equation, how fluctuating field respond to large-scale inhomogeneity. Okay? Just dropping such turbulence interaction. And another approach, my approach is I call closure approach. And rather than retaining this inhomogeneity, we would like to treat this nonlinearity, very elaborated manner. Then a fluctuating equation is written like this. This is actually the same equation for homogeneous turbulence. Okay. Then this R and S is some technical detail. This is so-called rapid term for pressure perturbation. This is so-called slow term. Okay, please. Oh, sorry. Bracket is in this case some mean. So ensemble mean. Okay. Sorry. Because we consider this type of decomposition of any field, then this is mean. So bracket means appropriate mean, average. Yeah. Actually, first we will consider evolution of mean. But in the evolution of mean, we have to treat turbulent correlation. And that part show up as this. Okay. Oh, in fluctuating equation, you will have this one. If you subtract Okay, so this is so first moment of U averaging can be considered as 0. But this U prime is not necessarily 0. Okay, this is just a kind of variance. If you have fluctuating motion, it is not at all 0. Is it okay? Capital U, this one, capital U. Capital. Yeah. Right. Yeah, so in Reynolds averaging case, for example, F equal divided into F mean plus F prime. And then if we take averaging of F prime, it is 0. This is the Reynolds rule for averaging. That means that averaging itself has a projection. So in this sense, this is the same as this. This is in the case of ensemble averaging or spatial averaging. Oh, what is the problem? Okay, so I don't remember. So where I did. So then in my case, I would like to fully treat this type of one. And very often quasi-linear approach is just neglecting the difference of these two. This is quasi-linear. Actually, I wrote this. And this is, in some sense, at the workshop in March, Brad Marston and Stephen Tobias talked a lot about quasi-linear. But of course, they need to treat some nonlinearity. Then partially incorporate some interaction between fluctuation. But in our case, we fully would like to treat that. But this is just homogeneous. Then we have to treat we have to consider how to treat inhomogeneity, starting with this one. Then we coupled some multiple scale analysis to this homogeneous equation. Okay. Okay, so and a long time ago in January, I talked about something related to plumes. And at that time, I talked about some convection conundrum. Then there are several approaches, and I talked about this. And today, I will talk about some rotating effect. And also, magnetic field is another story. And those who are interested in, please look at these books or a paper of mine. Okay. Anyway, today I will talk about the rotation effect, but not only in the convection conundrum situation. Okay. Then I will start in what situation eddy viscosity or diffusion approximation for turbulence flux cannot work. Okay. And first, this is very elementary description of turbulence effect. And this is a pipe flow or pipe flow. Then this is a very rare case. We know the exact solution of Navier-Stokes. Okay. Then we have a parabolic profile in the case of laminar. But if we start to consider turbulent state, then realization is much more random. Then averaged field, this is axial velocity profile, becomes much flatter compared to laminar case. This means that due to the very strong mixing effect due to turbulence, we have very flat profile at the main portion of the flow. All the inhomogeneity is located near the wall. This is a typical situation. Then, in this sense, large-scale structure is all smear out in the main part of the flow. This is a typical situation for turbulence. Okay. Then, if we start to consider eddy viscosity, again, this is mean field equation. Okay, probably I should have shown this one first, but this is mean field equation, and then this term show up. Okay, this is so-called Reynolds, which represents solo effect of turbulence on the mean field. Okay. Then eddy viscosity representation started by Bushine long time ago. He just considered turbulent flux of momentum can be expressed is proportional to the mean velocity strain coupled with some effective viscosity. It is called eddy viscosity. And Bushine himself did not present any expression for eddy viscosity. We had to wait for Prant's work in 1925 or something of mixing length expression for that part. But anyway, yeah. Oh, so because yeah, that's my understanding. So then, Bushine, you mean? Of course, he already started this type of decomposition for mean and fluctuation. Then in my understanding, due to the analogy with the gas dynamics, he considered some as you know, if you have molecular fluctuation, then it can be expressed this type of expression. So I think that's the main, what to say, not the motivation, but his logic. Yeah. So sorry, I did not answer directly to your question. But anyway, and also the same is the case for plant light. But anyway, if we just adopt or accept this expression, that means that turbulent flux is proportional to the mean strain, mean shear. This is a very big assumption or approximation. But anyway, this is eddy viscosity. Then substitute this expression here, then you will get this expression. So original molecular viscosity is added by effective viscosity, then nu plus nu tau. And I wrote in this form because very important point is that, first point is that nu t typically enhances effective viscosity much higher. So this is the reason why we have this type of strong mixing. Another very important point for me is that nu t itself has spatial dependence, temporal and spatial dependence. So this is the second point. Then otherwise, if nu t is just a large value, constant value, in such a case, you still have a parabolic profile because of the similarity of the equation itself. Then you may have this type of parabolic profile. But you have very flat profile. So that means that this nu t has a strong spatial dependence. This is very important point if you consider turbulent transport. Okay. Okay, so okay, then I will just consider probably I cannot tell anything about the subgrid-scale modeling. But anyway, then this is eddy viscosity. S is strain rate. Okay, du dx plus du dx. Okay. Then if we naively consider this is correct, then if we take R11, R22, and R33, then all turbulence intensity in three directions should be the same. So in this sense, if we naively adopt eddy viscosity representation for the turbulent flux, we just have an isotropic state of turbulence. Okay? But it is not at all the case. And for example, if we, another point is that if we just consider a more general expression for that part, shear, but transport coefficient is force of the tensor. Okay. Then this D just means that the deviatoric part or traceless part defined by this one. Okay. Then, and this expression can be written because velocity shear can be divided into a symmetric part. This is strain rate, and anti-symmetric part of shear. This is so-called vorticity shear, vorticity tensor. Okay. Then if we still consider this transport coefficient is isotropic, this is a very generic expression for isotropic force of the tensor. Then if you substitute this here, then you will again get this expression. So this means that with isotropy, the mean rotation motion represented by vorticity tensor disappears. So in this sense, eddy viscosity representation is highly related to isotropy of turbulence, and also neglect of mean vertical motion. This is very clear. Then, once we start to consider such anisotropy and vertical motion effect, mean vertical motion effect, then this eddy viscosity representation should not work. That point we can easily imagine. Okay. Then I will show just two examples. Very simple flow, but eddy viscosity does not give proper result. This is flow in a square duct. We just consider some duct, very simple flow. Then, of course, we have axial velocity profile, axial velocity. But in addition to that, we have this type of secondary flow. Okay. So, and usual eddy viscosity representation does not reproduce this secondary flow at all. This is why it failed. But if we consider mean axial vorticity equation, because this secondary flow represents some mean axial vorticity, then if we consider the evolution equation for mean axial vorticity, then this type of term show up. This is actually represents the anisotropy. So that means that if we have anisotropy in turbulence, then we may have some this type of axial vorticity. So in this sense, this is very important. And if we, again, naively adopt usual eddy viscosity representation, then all quantities written like this, then this isotropy state corresponds to this omega x equals z. Okay? Then we have to consider anisotropy of turbulence intensity. Then we have some mechanism which produce a secondary flow. Even with this very simple argument, we can recognize the importance of anisotropy. Actually, in the pipe flow or duct flow, we have axial mean velocity. Then typically the fluctuating motion for the axial direction is much higher than vertical direction. So in this sense, this type of anisotropy is very important to reproduce this type of secondary flow. Then how to implement such effect into turbulence modeling is the next one. Then this is Rij1 is just eddy viscosity representation. And 2 is nonlinear algebraic model. So if we adopt this type of expression for the second part, which gives the deviation from the eddy viscosity, then we write the anisotropy of turbulence fields can be written like that. Then, as you see, irrespective of V and W is vertical velocity, mean velocity. Irrespective of V and W, if we have this quantity, we have some possibility, we have some anisotropy. So in this sense, anisotropy will appear. This gives the possibility of secondary flow. So this type of model has long time ago presented by my mentor Yoshizawa and also NASA's people, Charles Spegiel, long time ago. And also some of Igor's work related to mean vortex generation by shear is, I think, essentially the same to this type of expression. This originally it was considered by engineering people. Then these people consider some derived such model by some statistical analysis. And in the case of Charles Spegiel case, he considered some symmetry. Then he derived this type of one. And actually, Spegiel mentioned that this part will not work, something like that, due to symmetry. But that's the detail. Yeah, that's right. And also, in engineering practice, people also consider higher order nonlinearity. So S, omega, S, omega, S, blah, 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 blah. Then it plays very important role. For example, channel with rotating, something like that. So in such a case, this type of higher order nonlinear model plays an essential role. This one. If it depends on how to derive or how to get this expression. So if we just consider some symmetry, it's a bit hard. But of course, but if we consider examine with our method, then we can get, including model constant itself, if we assume some spectral scaling, then we can get. And also there are several symmetry arguments. You can get several relationship between theta 1, theta 2, blah, blah, blah. But anyway, okay, this is so-called nonlinear algebraic model, okay? And which is related to the vorticity generation mechanism. Okay. And okay, so I already consumed half of my time, but then this is swirling flow. And today I would like to argue this swirling flow. And sorry, first I just told about the pipe flow. Then you will get this type of very flat profile, okay? But if you impose rotating motion in addition to actual flow, then situation changes drastically. Then this is the actual velocity profile if we impose typical profile of actual velocity. Then you have, as you see, you have dent in the near center line region. And this is the situation. So we, in addition to actual velocity, we impose pipe itself is fixed. Pipe itself is fixed. But utilizing some propeller or some vane or something, we also impose some rotating motion at the inlet. Then profile drastically. This is a rotating velocity. So near the surface, near the center region, you have a solid rotation. Then outer region, you have strainless rotation. This is typical. This is something like Taylor vortex or something like. But anyway, then the flow goes to the downstream. Then this relax, something like this, very similar to the usual pipe flow. But another very interesting point is that without imposing any rotating flow, just rotating the pipe itself, this is the case, actually rotating turbulent pipe flow. Then in such a case, that flat profile becomes a little bit similar to laminar case. Then people often call this is delaminarization, but state of flow is highly turbulent, not at all laminar. But you have this type of profile. This is experimental result. Depending on the rotation rate, original pipe flow profile becomes this type of. So then center region is, in this sense, accelerated. Actual velocity is accelerated. So then proper turbulence model can tell the difference between these two. Rotating the pipe itself. Okay. Because this is very strong turbulent pipe flow. So in this sense, compared to renormalization related to rotation itself, so this effect it should be attributed to turbulent motion itself. That's right, that's right. And actually, empirical, yeah. Yeah, this one. Or, yeah. This is so-called rotation rate. So it's so yeah. That's right. That's right. So in this sense, we have to omega rotation rate with multiplied by turbulence time scale. Then turbulence time scale can be written, for example, in the simplest case, is turbulence time scale is K total turbulent energy divided by dissipation rate. And then rotation, if I wrote rotation is omega, then you have to consider this one. And then omega epsilon. So then, sorry, I don't remember that scaling here. Yeah. Yeah. Actually, I will show in the next slide some basic analysis for that. Okay, so then this is the case for laminar flow. But if we consider radial momentum balance and also axial momentum balance, like that, then this is a centrifugal force and also pressure gradient. Then if these two are balance each other, then this is a typical case for strong rotating case. Then if you differentiate with respect to Z, then integrate with respect to R from 0 to center to some region, outside region. Then if you substitute this to here, then you will get this relation. This means that this is a evolution of center line velocity intensity. And this is an evolution of how to say, edge or coalition axial velocity, which is related to this rotating motion. Then the difference between the center line axial velocity and some outside outer region axial velocity profile depends on the rotation itself. The problem is that how this quantity evolves. Then we can easily imagine if we impose the rotation in the outer edge region. In such a case, most portion of the flow, you will get this gives a positive contribution. Then, because rotating velocity just gradually go to the central region like this. So in such a case, this one is bigger than h. So if you rotate, I mean the angular momentum is imposed from the outside in such a case. So we may have a kind of acceleration in the central region compared to the outer region. But if we impose rotation near center region, as I showed, so this is R, and this is And so this is a typical profile, as I showed. So this is R, and this is R inverse. So then vorticity, this is a U theta, and vorticity, UX or UZ. Actual vorticity is something like that. So then in that case, you will get, this gives a negative contribution. Then center line velocity is slower than the outer velocity, actual velocity. This type of argument can be done. Yeah. Which one? This one? Yeah. Then how it evolved along the actual direction?
Yeah.
This quantity. Then the problem is that, so in which direction this type of rotating motion is propagating from center to the outer region, or outer region to the center. This makes the sign of this quantity positive or negative. Yeah, then of course this is just not exact argument, but we can get some impression. So if you vertically consider some evolution of actual velocity intensity in the center and also outer region, then this just shows that evolution has some difference between the center and the outer region. Yeah. That's a very important point, of course. Then actually, this is just how to say, in this sense, hand wave argument, utilizing just very simple expression. Then that's right. Then we have to fix some, for example, angular momentum flux to the axial direction should be the same. Okay. Then, but due to, if, for example, we can consider some weak swirling case and very strong swirling case, but with fixed angular momentum flux in the axial direction. Okay. I can write it down in equation. But then if we have, again, some speculation, but if we have a strong rotation, then mass itself is pushed to the outside. Then this gives a higher angular momentum because mass. So if we fix the axial angular momentum flux, in such a case, we need some deceleration somewhere. This is in the center. So this is a very naive argument. Due to the strong rotation, fluid is pushed to the outside. The angular momentum, due to this effect, angular momentum increases. But in order to sustain the same angular momentum flux to the axial direction, somewhere we need some UZ should be reduced somewhere. This is the center. That's my another very how to say simplified argument. But you are right. We have to fix some condition. Okay. Yeah, but if we very, very roughly consider this one, then as I mentioned, the point is that in which direction such angular momentum or rotating motion propagating from center to the edge or edge to center. Uh-huh. Yeah. That point I agree. I agree with you. So this is just again very naive argument to get some feeling of this. But the difference between the actually rotating pipe flow and the swirling flow is where we impose the rotating motion. Actually, if we, as I will show in the next slide. You see this is the inlet region and this is the outlet, and upstream and downstream. Okay, then this is rotating velocity, and this is the actual velocity profile. This is center. Then in this particular case, we have this dent profile at the upstream region. Then, but as the profile moved to solid rotation profile, then we recover very flat profile as usual, just pipe flow. So in this sense, in this particular case, this rotation is if vorticity is written something like that, is propagating from the center to the outer region. In such a case, we have a dent profile. But if we change the initial profile, actually some experimentalists did it. In such a case, they get this type of acceleration in the central region. So this is okay, but this is very interesting subject. Okay. This is turbulent. And the previous argument doesn't contain any Reynolds stress argument. Then we have to argue in the case of turbulence, how much Reynolds stress contribute to such momentum transport, including angular momentum transport. That's another story. Okay, so I have 15 minutes or 10 minutes. Then this is just, sorry, introduction. Okay, anyway, this is a swirling flow and actually rotating flow. And then profile itself changes drastically. And in this sense, we can easily imagine usual standard eddy viscosity representation completely fails in this case. And even if we start this type of initial condition, boundary condition at the inlet region, if we adopt simple eddy viscosity representation, it immediately gives the flat profile. So in this sense, eddy viscosity is too dissipated for this type of rotating flow. That is obvious. Then in engineering practice, people just reduce model constant. Only 1% of the original one, something, or 0.1%, something like that. Then they are happy to reproduce, but not at all physical. So this is the situation. So even this type of very useful ubiquitous flow configuration, so usual eddy viscosity completely fail. That's the point I would like to say. Then I would like to address this problem with some physical argument with mathematical treatment. And probably I should skip that part. So this is some helicity pseudo-scalar, and which gives how much breakage we have in turbulence, like this. And pseudo-scalar, it represents, as you see, in the mirror-symmetric system, if we under inversion, mirror-symmetric system, we have the same one, but the pseudo-scalar should change its sign. Then that, as this consequence, pseudo-scalar in mirror-symmetric system should vanish. Like that argument here. And also, helicity is directly related to some topological property of turbulence itself and knotedness. Then, if we have some conservation of helicity or conservation of knot number, then it gives some constraint for the turbulent motion itself. And also, if we naively consider the cosine and sine relation, this part contribute to the mixing due to nonlinearity. So in this sense, if we have finite helicity statistically, it may contribute to some suppression of cascading or something. All these things can be considered, but anyway, and also there are some arguments. So high helicity region is related to the low dissipation something. But as far as I know, the relationship between helicity density and dissipation is tenuous. That is a result. Then engineering people quit considering helicity. But anyway, this was already experimentally also. Okay, then this is a very naive argument again. So if we start considering the vorticity evolution, of course, in the case of variable density case, we have this baroclinicity term. This contributes to the generation of vorticity. But if we start considering turbulence itself, then if we consider large mean vorticity, then this type of turbulent correlation show up. Then it can be called vortex-motive force. Well, of course, this is ponderomotive force. But in analogy with the electromotive force in magnetohydrodynamics, it's sometimes called vortex-motive force. And this vortex-motive force is, of course, this is just a curl of the original fluid equation. So this is exactly related to the Reynolds stress in this form. So then if we got the proper expression for the Reynolds stress, we can properly evaluate vortex-motive force, which gives the proper evaluation of large-scale vorticity evolution itself. This is a basic idea, and I will skip that part. I already in January I talked a little bit about our theoretical formulation. The introduction of two-scale and Fourier representation to the first variable scale parameter expansion and Gaussian introduction of green function and statistical assumption on the lowest order field. Then utilizing the DIA, we calculate any calculation. So this is very messy, but very straightforward. Very straightforward. Then I just, this is an introduction of two scales. Very important point is that due to this introduction, any derivative is written like this. So that means that if you have a very large scale inhomogeneity, large scale variation, it shows up with this delta. Okay, delta is scale parameter here. And again, if delta is very small, delta is not necessarily small in principle. But if delta is very small, in such a case, this capital X is suitable for describing slow motion, because only when this original x changes considerably, then capital X starts changing. So in this sense, if delta is very small, we have very nice scale separation. But again, important point I'd like to stress is that if we have a large scale inhomogeneity in time and space, then it shows up with delta. This is very similar to a kind of some asymptotic expansion, but this is derivative expansion. Okay. Not homogeneous. Turbulence itself is not homogeneous at all. But we will also consider some expansion from homogeneous state. Then this is the original equation, and this is solenoidal condition itself. And again, even for divergence U condition, have this type of additional contribution from the higher order. Okay. That's right. That's right. That's a very important point. So actually, this is very simplification. So this delta should be delta x, and this delta should be delta t or something. Then we can treat. So in my previous talk, I adopt double averaging in time domain and space domain. But systematically, we can, if we change this delta and this delta, then we can systematically realize such a situation. That's a very important point. But here, I just explained, I just adopted these two delta is the same. Okay. Then we expand the field. So zeroth order field is, as you mentioned, homogeneous field. And all inhomogeneity coming with this delta. And one delta corresponds to one derivative for large scale. So if you have delta square, it is S square or S omega or omega square, something like that. Okay. So in this sense, in principle, we can calculate all the field with this. Then here, lowest order field should be homogeneous. And here, we just assume isotropy. In addition to homogeneity, we assume isotropy. And this is a longitudinal and transverse and cross correlation. Then anisotropy show up. Yeah. Or not only rotation itself, but we will get some anisotropy with higher order contribution. That's the way. Then this is just in configuration space, we just consider this type. I will skip that part, but you can see on the book of, for example, Bachelor, you will see how to express isotropic velocity correlation. And this is the expression, and I will skip that part. Then in wave number space, it is written like this. And this part is related to solenoidal energy, and this part is related to compressional, dilatational energy. In this particular talk, I just neglect compressibility. And that part related to this cross correlation, which is directly related to helicity. Then, if we consider a mirror-symmetric system, we don't have this one. But once we start to consider non-mirror symmetry, we should retain this one. Then, how much and how this contribute to the Reynolds stress is the one. Okay, then we can calculate any turbulent correlation like this, then lowest order field just gives the energy information because the lowest order field is homogeneous isotope. Okay, so in this sense, lowest order field doesn't depend on any large-scale inhomogeneity. But from higher order terms, you will get strain rate and also rotation-related part. Okay, all such terms show up from the higher order. Then this is deviatoric, so then energy part is already subtracted. Okay, then in addition to that, we can evaluate transport coefficient itself. Okay, then this nu t, this is the eddy viscosity. Bushiness started to consider is written like this with green function and energy spectrum. Then this part, if we independently evaluate this one, this just gives the time scale. Sorry, this is response function, green function. So how much past affects the present state? This is the weight. Then if we integrate from minus infinity to the present time, this gives some time scale. And this part is time scale, and the other part, energy spectrum, spectral integral of energy spectrum just gives the energy. So in this sense, this gives tau u square in the simplest case. Then this is actually the mixing length expression. So this is a generalized expression of mixing expression. Depending on the G and Q, then we have the analytical expression for the eddy viscosity, which is a proportional coefficient for the symmetric part of velocity shear. Mixing length. L is actually tau u. Yeah. Okay. So I think your question must be how to evaluate mixing length. Yeah. Then you have some. You need some information of spectra. Then mixing length spectrum. That's right. Then we can evaluate what is the scale which gives the. Yeah.
So does Nuti doesn't know anything about rotation?
No. Here, no. Yeah. This. Yeah. This is a bit complicated. So originally this spectrum is related to zeroth order field. Yeah. So in this sense, homogeneous isotropic. But then, yeah. That's very important point. Then basic field is just for basic field, lowest order field. But in the real fluid turbulence, we have not at all homogeneity, not at all anisotropy. Then in this sense, it can, so in this sense, this is related to the renormalization of green function and correlation function itself. So a bit complicated. But original definition is related to the basic field. Delta disappears in the final result. At this stage, yeah, if delta is yeah, in this case, delta is just a scale parameter expansion, parameter for scale expansion. Then if you need to retain the higher order delta, that means that you need this type of eddy viscosity representation is not at all good. So we need some additional. This is just one derivative of mean velocity. So in this sense, if delta is not so small, in such a case, we have to sum up. Delta will not show up, here. But delta is related to how much terms we will calculate in the scale expansion. Oh, yeah. This is actually the case. So this is delta is only up to 1. If we take up to 2, then you get the previous one. Previous one S square and S omega and omega square. Yeah. But here, yeah. So here we implicitly assume. I just show eddy viscosity up to the eddy viscosity representation, not higher order nonlinear expression for related to S square or something. I don't show here at all. But in principle, we can calculate. But I think David's question is that how much we should retain. Again, it's okay. So it is again the very similar one with part asked to me related to this one. So then again, the important quantity is K over epsilon multiplied by S and omega blah blah. So in this sense, this is very big. That means that S is very large. In such a case, we have to, this type of truncation for the first order in delta is not good. So that already means that this is actually the first order. And the usual standard eddy viscosity representation just retains this part. So this corresponds in this formulation, the cut off at the first order in delta expansion. But not only S, but also omega show up if we retain in non-mirror symmetric part. This is the point. Of course, we can improve the expression itself depending on this parameter. So compared to, this. So then this is, if this is very strong, in such a case, this type of argument itself is in some sense dubious. I think I need some kind of argument like rapid distortion or something like this. This is the case. Yeah. But still, if you retain this type of eddy viscosity as a first approximation, it's already assumed in this formulation. So this quantity is not big. This is the situation. Then some truncation at some moment is not fully preferable, but not so much problematic. Yeah, if you accept this one. That's a situation. Yeah. Yeah. Okay. Yeah. This is the main part. Yeah. Sorry. Yeah, this one is a mean. Yeah. Delta nabla X, capital X. It is possible. It is the how much wave number for example helicity have, and the helicity itself is already u dot omega average to u dot omega. Yeah. Okay, I agree with you. Yeah. Okay. Then anyway. So in addition, if we retain a non-mirror symmetric part, we have this part. And then this is absolute vorticity, rotation, system rotation and relative vorticity coupled with gamma. Gamma is this one. And then it is not related to Q itself, but helicity gradient. So gradient of helicity. And then utilizing this analytical formulation, we can consider this type of turbulence modeling utilizing 1-point statistical quantity. And this nu t is related to, again, energy multiplied by time scale. And also this is helicity gradient. Helicity gradient coupled with this quantity. This is a model expression based on the previous analytical spectral integral and time integral.
Yeah.
That's right. And that's another story. We can treat. But anyway, okay, then if we adopt this expression and with this additional term, which is related to coupling of vertical motion, including rotation with helicity gradient, special gradient of helicity. Helicity itself is the averaged quantity already. Then, which even with eddy viscosity representation, with this helicity gradient term, inhomogeneous helicity term, we could reproduce the dent profile of this one properly. Of course, we have an additional term with additional constant. But this is, I think, much more physical compared to just reducing this model constant to just 1% of the original. Because if we don't have any helicity or any rotation, it's automatically reduced to the usual pipe. Yes. So far, we can evaluate some order by again assuming the spectrum of helicity. We can. But so far, it is not fully determined. We need some comparison with, for example, direct numerics with this model. This is turbulence model. And actually, in the next section of my talk, I will give you the real number which is given from the direct numerics by Axel Brandenburg. But this is, okay, so then I think I should finish. Then large scale flow generation. Then I just made this type of setup. Then ingredient is rotation and inhomogeneous helicity. Okay, okay, that's very important. Then with Axel, we did some numerics. Then by hand, by external forcing, we impose inhomogeneous sinusoidal helicity from the beginning until the end of simulation. Then at the initial stage, we don't have any large-scale flow by setup. But as time goes by, with this setup, again, rotation and inhomogeneous helicity, that's all we impose. Then large-scale flow is generated. Then we compare the direct numerics with Reynolds stress with these modeling terms, model terms. Then at the very early stage, we don't have any large-scale flow. Then we just compare this one with this rotation term coupled with the helicity gradient. Then this is Reynolds stress itself. This is the helicity gradient term. So we have a rather good correlation between these two. And at the developed stage, we already have a large-scale flow. Then we can expect the balancing between eddy viscosity and this rotation-related helicity gradient term. Then we compare these two terms. Then this is very nice correlation at the very developed stage. Developed stage is here, something like that. And early stage, so this shows that we need some additional term, which is related to helicity gradient and rotating motion. Otherwise, we cannot reproduce Reynolds stress at all. This suggests. Okay, so then I consider some application to because this is a tropical cyclone. There is an upflow and downflow with rotating, not tornado, cyclone. This means that so near the eye wall, we have a very strong helicity gradient, mean helicity gradient. It suggests that we have also fluctuating turbulent helicity may have a strong gradient here. Then actually, strong flow generation is observed near the eye wall region. Then I would like to apply this one. And another possibility is solar convection zone. And then here, as you know, we have a prograde velocity profile. Then this is an angular momentum equation. And this is the helicity related contribution for angular momentum. Then speculation is that helicity is something like that, as several numerics shows. Then we also have a meridional circulation like this. Then vorticity associated to meridional circulation is from screen to U. Then if helicity, Laplacian of helicity is positive, in such a case, we can expect the flow induction from U to the screen. So this is good for reproducing this type of prograde profile. Then I asked Mark Misch to check this quantity, helicity itself and helicity gradient and vorticity, and compare it with the Reynolds stress in his calculation with this helicity effect. Then, at least if we adopt solar parameters, the Reynolds stress, magnitude of Reynolds stress is comparable with this helicity effect. So in this sense, it is not hopeless, not hopeless. That's all. But okay. Okay, so probably I should finish here. Yeah. That's right. And especially near the, yeah, that's right. That's right. That's another point. Yeah, you're right. Okay. Thank you very much. And yeah, I will finish here. Thank you for your patience again. Yeah, yeah. That's very important, good point. Then helical property itself doesn't directly related to the compressibility itself. Compressibility. Yeah. In a simplest case. But if we start to consider the angular momentum transport with this helicity effect, in such a case, so compressibility, of course, modulates how much helicity works for this case. But I have no idea about that. Yeah. Yeah. In all I can say is that if we consider dynamo-like effect, I just mentioned that Reynolds stress, but also we can consider the electromotive force. In such a case, inclusion of helicity with compressibility plays very important role for dynamo effect. That's another story. But I cannot say that point. Actually, we just started such type of argument with, for example, Pablo Menini with stratification, not strong compressibility, just stratification. Not necessarily anelastic. No, yeah. Yeah, anelastic in the sense, yeah. Okay. That point yeah, Aka itself is, as you know, for the theory for very low Reynolds number. Yeah. So then it is rather related to the first approach of instability or large scale instability argument. Yeah, actually, in the paper with Axel Brandenburg, at the appendix, I compared the Aka effect with this effect. And also in the mean field community, lambda effect by Günther Rüdiger and Günther Rüdiger is okay, and Kichachinov, I think. then I compare these two effects with this effect. And the main point of my to the Aka effect is Aka effect is just for weak turbulence case. Structure itself is also again this is in terms of helicity, and the Aka effect is just in some sense for me it's a kind of rapid distortion or something with not so strong turbulence. Yeah, that's right. Aka doesn't need helicity. Doesn't need helicity. Yeah, that's a big difference. And Aka is in this sense a bit similar to the higher order effect, as I mentioned. So S square and S omega. That is just to need anisotropic. That is the reason why Aka is Aka. Anisotropic kinetic alpha something. So they need anisotropic. In this sense, very similar to the higher order contribution, but without breakage of mirror symmetry. That's right. Yeah, I only read the Uriel's original paper and something other. So, but in my understanding, yeah. Okay. Thank you for your patience.